Yeah, so today I'm going to tell you about this work we did in November with Kanado Godo, who is a postdoc at Cornell, and my PhD advisor, Tom Hartman. Um, so let's get started. So in the context of black hole information paradox, the entropy of Hawking radiation plays an important role. It quantifies how much information is lost, and as we've learned over the past 2 years, there's a new prescription for how to compute this um, entropy of radiation, which is this island formula in the presence of gravity. And this is a prescription which gives us the answers consistent with unitarity, and it solves the page paradox for us. And it only uses the low energy physics. It doesn't use any input from UV. And it's kind of intriguing that such a formula exists, and given that computing von Neumann entropy for quantum systems is, generally notoriously hard, but once gravity is included, there is such a prescription for it. So, as you may have heard many times, this formula in some toy models is derived from replica wormholes. So these are the wormholes that are appearing in the replica trick when we try to compute trace of rho to the n. So for example, for trace of rho r squared, we expect a cartoon like this, where the gravitational regions are connected. And one way to think about the replica wormholes and replica trig is that it provides a shortcut to compute the entropy without telling us what exactly the density matrix is. And this is something that, it's familiar from quantum fields as well, like in 2D CFD, the same thing happens. So without knowing exactly what the density matrix is, this method will tell us what the entropy is. And although there has been a lot of work on using the island formula to apply it in different setups, for example, in cosmology even, there has been little work on like actually constructing these replica wormholes. And, there are questions that one can ask, like basic questions like, what's the causal structure of these replica wormholes, or whether or not they're traversable. So these are some basic questions that we can address. But for some reasons, they're not that easy. So for today, I will focus on n near 1, which is relevant to derivation of island formula. And even in that case, the derivation is a bit formal, at least in these two sense. One is it relies on Euclidean methods. So it seems that the first step to define replica wormhole is to consider Euclidean path integral. So it seems it excludes some interesting black holes, like black holes formed from a collapse. Also, the derivation relies on the local equation of motion near the mouth of the wormhole or quantum extremal surface. So one might worry a little bit whether or not even these geometries make sense near n equals 1 globally. And these are not super serious issues, but it's nice to have some models that we can analyze these time-dependent situations. There might be other more serious issues, whether or not, where gravity is everywhere turned on, whether island formula makes sense or not. I'm not touching upon those. And I should say that there was this interesting paper in December by Davis and Santa Barbara group about like trying to set up the problem directly in Lorentzian time. But yeah. So the goal of my talk is basically to find this formula using the Euclidean path integral for a black hole which forms from a collapse and then it evaporates. So for these time-dependent black holes, we want to find the replica geometry and replica wormholes. Okay, so that's the goal. I should say that even before constructing the replica wormholes, we need to fix a background. We need to find a background that we want to work on. And one of the popular set of, one of the toy models that often is used in the past 2 years is these models where there's a gravity and there's a non-gravitational region, and we just glue them with some transparent boundary condition. And you can do this gluing both in Euclidean signature, or you can just evolve it in the Lorentzian signature. So this is, for example, the zero temperature um, black hole glued to the flat spacetime. And actually, there was the first paper that they started, one of the first papers which started the whole development was this paper by Almeri, Engerhall, Maxfield. So they used some quench setup where they had some like ADS2 geometry and some flat space geometry that they weren't in contact with each other. So this is the Euclidean picture for them. And then at some time, some small Euclidean time, they become in contact with each other. And once they look at this and they went to Lorentzian signature, they basically claim that the effect is that these flat space and gravitational region, they weren't in contact. At some t equals 0, they became in contact. And that being, when they become in contact, the effect is that there are shock waves produced. And one of the shock waves which goes inside the black hole increases the mass of the black hole starts to evaporate, and that was the setup that they considered. Is there a question? No. And there was a little bit of puzzle for us for these type of models, because in the East Coast replica wormhole, when we also analyze the similar problems. So the way in AEMM, they considered the Lorentzian evolution, and they found that in the Lorentzian signature, everything seems to be local, like the equations governing this x of t, which is the variable in Schwarzian theory, that was local. Everything seems to be local. However, when we analyze these type of problems in Euclidean signature, we realize that gluing this gravity region to non-gravitational region in general is a hard problem, and it involves solving conformal welding problem that I will explain a little bit more. And this problem in general is non-local unless you have some like very symmetric situation like eternal black hole, then it's easy, but otherwise it's hard. So one puzzle we had was like, how is it that they found these nice local equations, but it seems that from Euclidean perspective, this is such a hard problem. So how does this work, and how do they find this nice local equation? So that was also a puzzle, not necessarily about the replica construction, just about like understanding the background from the Euclidean perspective. Okay, so with these two things, this is the outline of my talk. So I will first tell you a little bit about this background that we're going to use in Lorentzian signature. And then we will go back and find how to find this background from Euclidean path integral. Once we know that, we can now start to thinking about this replica geometry and construct the replica wormholes for these evaporating black holes. So that's the outline. Okay. Is there a question? No. So let's start with the eternal black hole, because it's simpler. So our theory is always this JT gravity coupled to some large N CFD. And when we talk about the gravity dynamics in JT with the topology of a disk, all we mean is to find this x of t, which is this boundary curve motion as a function of this flat space-time. And in eternal black hole, it's very simple. There's no flux of energy. So the Schwarzian equation of motion will tell us what the background is, what we expect for finite temperature. This is a black hole in finite temperature. And that's indeed what we find for x of t. So how do we find the black holes that is evaporating? We can basically repeat the same thing as AEMM. So what we do is we consider two shock waves that are Z2 symmetric in time. And, once this shock wave goes into black hole, the same thing happens. The only thing that is changing is now the mass of the black holes, of course, changes. And there will be a flux, and the stress tensor of our matter field near the boundary point will have different contribution. There will be a delta function due to the shock wave. There will be some constant because the background is a thermal background. And more importantly, after the shock enters the black hole, there will be a term which is decaying, and it's the Hawking radiation. So we will get back to this and how this is derived. But here I'm just telling you the equation in Lorentzian, then we will go a little bit deeper in Euclidean. And once you solve these equations, the mass of the black hole has this simple behavior. So it's in the beginning, it has this, once the shocks haven't gone into the black hole, it has a value which is set by the temperature. And after the shock, the mass goes up and then it decays, and finally it goes back to the original, the value at that temperature. So that's the setup in the Lorentzian signature, but maybe I should see if there's any question or not. Okay. Yeah, so let's now go and see how do we.
Shiraz, you're muted.
Can you hear me?
Yeah.
Okay, sorry. Just to understand your setup. So the field theory outside, you're starting with the black hole at some initial temperature, and the field theory outside is at the same initial temperature. Is this right?
Before the shock enters, that's the situation.
And then you put this shock. So one of the shocks comes from the field theory. That's the shock going in. Where is the guy going out, please?
You mean this one? Oh,
yes.
We don't have to necessarily put that. Because I'm gonna get this from the Euclidean path integral, we need this Z2 symmetry.
So you're making it sort of time symmetric. Fine. Exactly. Okay. And then you say then the field theory remains at its original temperature. The black hole heats up and then starts Hawking radiating to reach equilibrium again. That's
basically like the one of the set of mode, like the left moving or right moving, I can't get this right. One of them will remain in the same temperature, but the other set of modes, they're not in a particular temperature, so their temperature will change as well. And
okay, thank you.
Black hole.
Yeah.
Can I ask another question? So,
sure.
Well, it seemed like I would have to do something very special to the coupling between the two systems in order for the shock wave to be completely transmitted. I would think that if I sort of set up some random boundary condition that's coupling two systems, there would be both a reflection and a transmission amplitude every time the shock wave hits the boundary. So is there something being done to make sure that any shock wave you send towards this interface is completely transmitted?
Yeah, that's a very good question. I think one reason for this is that because our setup is two-dimensional, basically, like things are factorizing left moving and right moving, so there won't be any reflection. But beyond that, I don't have a good answer. That's what we're gonna find from Euclidean path integral. But yeah, you're right that we can imagine a situation that some part of it is also, like if we give more dynamics maybe to the boundary curve, or like do some extra thing, in principle, some part of it could come back. But at least it seems that this solution that I'm explaining is consistent with equation of motion, meaning that if you just analyze the equations near this point, for example, and try to see whether the conservation of energy is respected or not, in that regard, things seems to be consistent. But whether or not there can be another solution, I don't have a good answer. That's a good answer.
Yeah, well, you sort of operating under the assumption that stress energy is completely transmitted across the interface.
Yeah.
Like if I decouple the two systems, then any shock wave you sent towards the boundary, either from the left or the right, would be completely reflected.
Right.
So if you turned on some weak coupling between the two systems, I would expect it would mostly get reflected. So one must be doing something special in order to get it completely transmitted.
Yeah, that's true. but I don't have a good answer.
Okay.
May I ask a question which is perhaps related?
Yeah, sure.
So, so what's it? So in the bath region, there's perhaps some matter field like a massless scalar field or something.
Mm-hmm.
So what is the boundary condition that you use at the place at the gluing curve? Is it like a Neumann boundary condition, or what's the boundary condition that you use?
Yeah, on the gluing curve, the boundary condition is a transparent boundary condition. So we basically like allow matters to come and in. It just we will preserve that the field should be continuous, and the conservation of energy should be respected. But besides that, things are transparent. So things can come in, like things can come in from both sides and they can go. And as far as the energy conservation at this point is respected, things can come in and go back. But what we're gonna do is we're gonna get this from a Euclidean path integral, and I think in Euclidean sense it will be more clear what we are doing, like what's the boundary condition. But yeah, it's basically completely transparent, meaning that fields are continuous and we can just.
So it's like one of those conformal boundary conditions which you use in a conformal field theory with a boundary, so that no, sorry, I take that back, because there you don't allow for energy transmission. This is not for any. Yeah. So I'm still confused about. So
I think, Gautam, it's like having no boundary condition. It's like imagining that you've got a background metric on your space. It's ADS on one part, flat on the other. Maybe imagine that there's some slight smoothing of that transmission. And then you just look at a conformal field theory propagating on that space. Don't think of that as a boundary, I think is what he's saying.
Don't think of that as a boundary.
It's just a change, a varying metric, a space with a varying metric on which fields are propagated.
Right. Right. Okay. Good. Yeah.
Thanks.
Got it.
Thanks.
Is this right, Amr?
Yeah. That's exactly right. Okay. So now let's go to the Euclidean preparation of the same background. So let's start with just the eternal black hole, because again, it's simpler. The way we prepare the path integral for eternal black hole is like, okay, this is infinite temperature, so we start to prepare our fields in a cylinder, and the gravitational region will map to like a disk. So this will be basically a hyperbolic disk. And if you use this map, we can also map it to a plane. So there will be, this is non-gravitational region, and we know the metric in the gravitational region. And in this case, there is no gluing. Like basically, you can think that there's no boundary, even though that the metric here and metric here is different. But the gluing is trivial. So what, like, if this wasn't green and white, then that will be the gluing. So this is kind of the trivial case. And when we go to prepare the black holes formed from collapse, there is a known way to do this in the literature, which is basically you insert two local operators in the path integral with some offset, and this is like called local quench protocol. And it's known that once you have this operator insertions, when you look at this setup in the in the Lorentzian time, you will have two shock waves, like a right moving shock waves and left moving shock waves. So they produce for you these shocks. The only difficulty is like, so here I, for example, wrote down the energy of that shock in terms of the scaling dimension, and let's assume that the operators are scalar. The only difficulty is that we can't really glue these manifold right now, like the gravitational region to non-gravitational region, because unlike the eternal black hole that you can guess it's the trivial gluing, it's trivial. Here it's probably non-trivial, so we can't really glue at this stage. So let's see how we should glue this. or what does gluing mean? So gluing just means that you want to have one coordinate which covers both the inside region and outside region. So that's and it is continuous across time. So that's what gluing means. And here for the inside region, we know, for example, what the metric is because it's supposed to be hyperbolic. So this is the metric. And outside, we don't even have a gravity. So metric is whatever we want. And basically the question or this problem of conformal welding is how you basically do this gluing when the theta, which is the boundary of the gravitational region, versus tau, which is basically parameterizing the boundary of non-flat region, that theta of tau is non-trivial. So that's basically the question. And if you just have one theta of tau, there are many ways that you can just extend this coordinate v or w from, let's say, v from outside to inside. So you can just write it explicitly, given theta of tau, what the coordinates inside w and w bar are in terms of v and v bar. However, in general, this coordinate extension is non-holomorphic, meaning that w and w bar, they both depend on v and v bar. And the problem is, in this type of background, we don't know what's the one loop determinant of our fields. So let's say you have like some massless fields, bunch of decoupled massless fields. You want to calculate their one loop determinant to calculate the stress tensor due to these fields. And we don't know how to do this. So instead, the strategy is to look for holomorphic extensions, which means that instead of trying to extend v coordinate to inside, give up on v, let's go to a third coordinate, let's call it z, where in z coordinate, everything is glued to each other. And there will be holomorphic maps from inside and outside, which in general, they're different. Let's call it f and g. And these f and g are basically equal to each other, meaning that the coordinate z is covering everywhere. So it covers inside and it covers outside. And the idea is that these maps, f and g, they always exist, so you can find them. And this is basically this problem of conformal welding, finding these two maps, f and g, such that they satisfy basically these conditions. And the advantage is if you can find them, then you can see that the metric everywhere in the z-plane can be written as some conformally flat metric. So this will be true everywhere in z-plane. And once we have this type of metric, we know how to calculate the stress tensor. We know how to calculate one loop determinants of our massless fields in this type of background. It's just given by conformal anomaly. So we can go from this metric to flat metric in z-plane. It's a plane. So once we remove it, we can compute the stress tensor. And this is basically the strategy to find the one loop determinants. And the gravity part is not that difficult for constructing this background, just calculating what the effective action for our fields are. That's the difficult part, and that's how we're gonna do that.
Sorry, could I ask a question?
Yeah.
Just so I understand, like in the above picture, like the top picture, is the gluing everywhere in the circle, or is it just close to the time reflection surface?
No, it's everywhere. So you should think that there's one surface here which is parameterized by theta, and there's another curve nearby which is parameterized by tau. And you given a general theta of tau, which is gonna go into your gravitational equation, you wanna do this gluing.
And could you explain why that is the case? I mean, I would have thought that if you're just sort of if the physics is that you're coupling these two systems at say t equals 0, then I would have thought that you want to just glue them together in Euclidean signature near the time reflection symmetric surface. But okay, could you just explain why a little bit? This is the right thing to do?
Well, the way we create these geometries is to first prepare the state using path integral.
Correct.
And once we construct that, I mean, the goal is to like first construct theta of tau in Euclidean and then find the Lorentzian evolution basically by analytic continuation. The problem is, at least we don't know exactly how to do this directly in Lorentzian. If you are
I
able to
understand.
do this directly in Lorentzian, then you're absolutely right. You don't have to do that. Like you don't have to go all the way to Euclidean evolution.
Mhm.
But the strategy here was to do it in Euclidean and then go to Lorentzian.
Yeah, I understand, but I would have thought that even in Euclidean, it would be sufficient to just glue close to the time reflection symmetric slice and not everywhere. That's the only thing I'm confused about. But why don't you go on? I don't want to hold you back.
Okay, sure, we can.
Sorry, I have a more elementary question. In these diagrams that you're drawing are just in the conformal field theory on the boundary. Is this right? Oh, sorry, it's okay. It's the whole bulk. Sorry. Yes, and how is the fact that gravity is dynamical put into your conformal welding problem? How is the fact that gravity is dynamical in the disk region put into this problem?
Well, the only thing is like this theta of tau will finally determine by gravity. So there's one piece of the gravity that I already solved, which is what is the metric in this W plane. That's like, okay, this is like, we can find it from the fact that the curvature, you know, it's -2. So we can find that piece, we can find the metric, but the remaining degrees of freedom is basically what the theta of tau is. And that's something that finally will be determined by the gravitational equation.
I see, but what about that shock wave that was going into the ADS region? Doesn't that change the metric and make it non-ADS in some part of the Lorentzian geometry?
No, I think the metric will still remain ADS because that's one of the equations. Like it will be hyperbolic metric, but this theta of tau, or you know, the corresponding variable theta of t, let's say when we go here, when we analytically continue this theta of t, this will have a jump. It will turn out as we go in Lorentzian.
So then I think I haven't understood what this purple shock wave is. Is that a shock wave of some matter field?
Yes.
I see. You're saying even if there's matter, the metric just remains ADS, and that's just because of the sort of dilaton equation. I see. Thank you.
Exactly.
Okay. Thank you.
Yeah. So,
yeah, may I ask? So
yeah.
I have some question, perhaps related to Omkar's question. So this is if I was in Minkowskian geometry, then this welding that you were talking about is the same as junction conditions in gravity, like the one that you use for the Oppenheimer-Snyder solution. Like you have Schwarzschild outside and the cosmological constant inside, and you match the metric across the boundary, but that's the whole boundary, including space and time. So
no, it's actually worse than that. I mean, this is just the fact that you're trying to compute the part that you're talking about is about like what's going on with metric and like whether it's like continuous or like first derivative. But this is just about like, this is a problem for computing the matter contribution in a whatever background you're going to choose. So in this background, where some part of it, it's like gravity, some part of it, it's non-gravity, you want to just calculate one loop determinant. But the problem is because you have this non-trivial identification, which you will have also in Lorentzian, we want to like calculating that part is the hard part. So it's not really about like the metric itself. It's the hard part is about calculating just one loop determinant. And the way that we do this is we go to Euclidean. We know the boundary condition in Euclidean. We know, for example, as we go to infinity, you know, fields should die off, and we know all of that. So in this situation, we know what the one loop determinants will be, basically from conformal anomaly. And then we can go back to basically your point that, okay, even given that this will produce some stress tensor, what will happen for the metric and like, you know, this junction conditions that you mentioned. But all of these, like this slide is just to calculate that stress tensor, which is going to source the geometry.
So I'm sorry, Amit, I'll ask one more stupid question. Just in your mathematical problem, where does the location of these psi insertions go into your problem?
Yeah, good. So the psi insertion, this V plane is like the original plane that we start with. That's like outside is QFT, inside is gravity. So we will choose where we want to insert them in the original V plane, which we started with. But in the Z plane, once we want to solve this conformal welding, they might map to another points. Like from beginning, we don't know where do they map at the end, but we will determine them like in this picture where we want to put them, and basically where we put this distance will tell us how far they are in the original manifold. That's
right. What I was trying to understand was that what I understood from what you said is that if you didn't have these insertions, then the answer for your V of theta was a trivial one, right?
yes.
That it was just. So how is the presence of these insertions, where they're located, how is that changing the conformal? Where does that enter into your equation?
Great. Yeah. So let me just go to the next slide. Maybe that will clarify a little bit. So the idea is that, if once we solve, let's say once we solve these maps F and G, so we will find this conformal factor, and then it's not hard to calculate the stress tensor. Basically, what we're going to do is to strip off the conformal factor using conformal anomaly. So then we have just some Z plane, which is flat, and we have two psi insertion. So in this background, we know what the stress tensor is. It's just some 3-point function. So in this background, we know what's happening. So then we can just go back and calculate the stress tensor in the original manifold. So there will be a piece from the, in the Z plane where it's flat, and then there will be this piece from conformal anomaly. So the idea is that this is just a stress tensor. And just quick answer to your question, Shiraz, is that when there's no psi insertion, we know beforehand that there is a solution for this problem. The solution is basically everything is trivial. But once you have psi insertion, you have to just consider the general problem that this theta of tau can be non-trivial because you have this extra psi insertion. So you have to set up the equations for a general problem. And then, okay, the solution might be simple. But here I'm just saying that, like, in the most general case, that you might have any like crazy, I don't know, sources in the plane, how to construct them. So this is kind of the strategy.
And the final condition you will put on this stress tensor is what? That it's only ingoing or only outgoing or something like that? I mean, I'm trying to understand what condition you put to determine what is the good map.
So you have to kind of solve all of them together. So this so far is just assuming that you find the solution of F and G, what the stress tensor will be. But you're right that the solution of F and G, they depend on this map theta of tau, which ultimately is gonna be evaluated by the gravitational equation. So in a way, they're all connected. I'm just saying that, like, if you first assume that you're given a theta of tau, and then you solve for these two maps F and G, then this is the stress tensor you will find in terms of F and G. And then this stress tensor has to go into the Schwarzian equation of motion to determine theta of tau. So that's how this problem is very non-local, because these maps are non-locally related into theta of tau.
I see. So your final equation is this. I'm sorry to go on, but is that your theta of tau obey the equation of motion that comes from the Schwarzian? Is this right?
Yeah, exactly. So the
equation now I understand. Thank you.
Equation will be something like this, like TVV minus like TV bar, like at the interface. So in this final equation, the variable will be this theta of tau, but the stress tensor which goes into this equation will depend on this function f, and it will depend on whatever source we're gonna have in this E-plane. So that's kind of what will happen.
Thank you. I understand now. Thank you.
Yeah. Okay, so without going like into too much detail, I just want to say that this welding problem is in general a hard problem because of all of these like non-local connections between F and G and theta of tau. It's on the same level of difficulty as like Riemann uniformization theorems that you want to just map some like random shape to like unit disk. But there are cases that it can be solved. So one of those cases is when we have a perturbation. So for example, if you imagine that the energy that you're sending into the black hole is very small, then in that case, we can solve this because this profile theta of tau that I was talking about, it will have some deviation from the theta from tau, which is just a eternal black hole. It's a trivial solution, and you can just use this equation and solve them. It's not super important like the details here. What's important is it can be solved, and in general, the solutions given delta theta of tau, of course, this maps delta F and delta G, they depend on delta theta of tau. And in general, they also have some projections into positive and negative modes. It's just because F and G, they are holomorphic in different domains. One is holomorphic inside, the other one is holomorphic outside. So you will get also some projections to just pick analytic piece of, like, for example, your delta theta of tau. So that's basically what happens. And now, as we discussed in the previous slide, now when you feed this into the equation of motion for gravity, you can solve for this delta theta of tau, or you can solve for the mass delta, change in the mass of the black hole. And this is what you get. So the mass of the black hole will be given in terms of basically two pieces. I call them positive and negative pieces. These are these blue and red pieces, and the mass of the black hole is just sum of these two. So this is what happens. And the fact that there's positive and negative frequency modes is that this delta F and delta G, you have to pick some positive modes in one of them, and for the other one, you have to pick negative modes. So at the end, the mass of the black hole will be the solution of two different set of modes. And this is, for example, the plot for given offset. Let's say delta over L, this is L equals 1/2. So, and everything, the energy of the shock here is small. So this height of the mass is very small. And in this limit that we can solve this welding problem perturbatively, we can see what will happen as you decrease the offset. And what will happen is these two solutions, the region that they have overlap, it's just getting smaller and smaller as you send this offset to be 0 while you keep the energy of the shock to be still small. So as you do this, this is what you find. And as you send this offset to 0, what we found is that we find there's no mixing between these two types of solutions, these negative and positive modes. And this is something that can only happen in Lorentzian signature, because in Euclidean signature, if your mass has like e to the I tau, it should also have e to the minus I tau, because you want things to be real. But in Lorentzian signature, you can have this situation that you have solutions that are decoupled, like modes that are decoupled, and it's still everything is real. So that's what we found. And
yeah, sorry, I didn't understand where in your mathematics you went to Lorentzian signature. I thought you were just working with the Euclidean problem.
Yeah, good. So we started here from the Euclidean. We started from Euclidean, and then you have these equations that still are in Euclidean. But once you solve them, you have so the way we solved it is first we project the whole differential equation into positive and negative frequency modes. That's the easy way to do this. And once you project in Euclidean, you can just solve both of those equations separately. And so that will give you some function in Euclidean. Now that you have those functions, you can now go to the Lorentzian. So this is just a solution in the Lorentzian. So we basically solve this mass or x of t or theta of t in some Schwinger-Keldysh contour. So we start with Euclidean, but then we evolve them in Lorentzian. And that's basically the result in Lorentzian.
Thank you.
Yeah, sure. So one of our main observation was that because these modes, like these positive and negative modes, they're not coupled to each other as this offset goes to 0, actually this allows you to solve this welding problem to all orders in energy. So the previous slides was for the small energy that we can treat this perturbatively, but what we observed is that if you have this condition that delta goes to 0 and these two solutions, they don't talk to each other, then you can solve the conformal welding to all orders in energy. And you can find, so you don't have to consider the E psi to be small, just fix the E psi. And in this limit, you can actually write down the solutions in Lorentzian for these functions f and g, because in Lorentzian, this function f and f bar, they have different analytic continuation. You will find two functions, but the important thing is you can just solve this conformal welding in Lorentzian. And
sorry, offset means the distance from the insertion from t equals 0?
Yeah.
And so when you take that offset to 0, you simultaneously take the amplitude of the insertion also to 0 to keep the energy fixed? Or something
Yes,
like that?
exactly.
Okay, thank you.
And actually, what will happen is that the Hawking radiation term that I previously wrote, which allows the black hole to decay, is this welding contribution, is this welding stress tensor. So this is kind of interesting, at least it was for me in the beginning, because in the previous, like in the East Coast paper for Replica wormhole, this conformal welding seems to play no role. It was something that, okay, it's an artifact of the model, it makes everything complicated, and still I think it makes things complicated, but it's just interesting that if you just do this, like, and consider everything in Euclidean, and then analytic continue in Lorentzian, then this welding contribution gives you exactly the Hawking radiation term that in the Lorentzian part I wrote for you. So it's just something that seems to be consistent. And note that this plot for m of t that we find at the end is basically the same plot we found in the Lorentzian discussion. So because once you take this offset to 0, these solutions, they didn't have any overlap. So they look like this plot. The only thing which changes is, this in the previous slides, this the energy of the mass had to be small because we were working perturbatively, but because we found this solution to all orders in psi, then now this height could be anything. So this is exactly what we found in the, in the Lorentzian section. Okay, is there any question? I think there was. No? Okay. Great. Yeah, so this kind of solves the puzzle that I stated about, like, how the AEMM they get their equation. I should say that we don't say that the AEMM equations were wrong or anything. Especially in Lorentzian signature, they wrote down some equations which, that it was the solution of equation of motion. But the problem is when we want to define the replica wormhole, we need to start from Euclidean path integral. So we need to also understand the background from the Euclidean point of view. So that's the difference. That because we want to go finally, like in next slides, to the replica wormhole, we need to start with the construction in the Euclidean time.
Yeah, maybe let me ask this. Could you expand on this thing? Statement that Hawking radiation is the welding contribution to this test. Can you just expand on that a little bit?
Yeah, so it was kind of quick, but if you remember previously, I wrote, for example, the stress tensor in the original plane, and it has some pieces. It was like something like, I don't know, TZZ plus something like C over 12. f of v and v.
Hmm.
So in the Euclidean, you have these two terms for the stress tensor, outside.
Yes.
And what will happen is this term, which was the stress tensor in the z-plane, which z-plane was the flat z-plane.
Mm.
In that case, this will be giving you exactly the delta function due to the shock once you take this delta goes to 0. And this term, which was coming from this conformal anomaly,
Hmm.
that term exactly gives you the term responsible for Hawking radiation. So that's kind of in a nutshell how you find this term. And this was the term that, in the Lorentzian discussions, so I have to go a little bit back. When I wrote here, this is exactly the same term that I was writing here.
Hmm.
Um,
I see. And all of this you can do without saying anything about the constituents of the bath. I mean, whether it's a scalar field, whether it's you don't need to know the the matter that constitutes the bath, right?
yeah, so the matter, we assumed it's a CFD to use this equation for conformal anomaly. But beyond that, the only thing we assumed is that once we construct this in Euclidean, the boundary condition at infinity goes to 0. Like that's kind of the only thing we use, because that's when you use this conformal anomaly, I think that's kind of assumed that your fields are given at infinity. And if you have a CFD, then you can use this conformal anomaly, and its contribution to a stress tensor will be given by this type of Schwarzian derivative. So so at this stage that this central charge appears, I use the fact that my field is a CFD, but that's the only place.
And sorry, the C here refers to some CFT that's in the ADS2 region or in the bath or what?
In both.
Is there any requirement that the central charges match?
No, I think you can consider more general case, but we just use basically this transparent boundary condition for as far as the matter is concerned. We assume that, it doesn't see this boundary, as Shiraz was pointing out. So that's why we consider the same CFD on both sides. But yeah, you're right that we can also, in principle, we can consider that you have some CFD here, some other CFD, and then you can impose some, good boundary condition.
Okay, thanks.
So that will be a matching condition, right? I mean, even if it is the same conformal field theory in the green region and in the white region, to ensure that it's transparent, I mean, this is like, okay, as Shiraz said, it's like in a propagation in a space-time with a varying metric. But if the metric has a jump or something, then you have to ensure some kind of a matching condition, like the value of the scalar field and the normal derivative of the scalar field should match something, because right. So that all is being assumed in order.
Yeah, absolutely. So the idea is like, if you map these original planes to this third plane, where everything is continuous, in this third plane, your matter, they don't see any boundary. Like in this third coordinate, the only thing you have is that you have some matter with a conformally flat metric, and they don't see this boundary. All of this information about this theta of tau, all of those will be encoded in this conformal factor. But on the z plane, everything will be continuous, so they don't really see the
Got it. Thank you.
Sure. Okay. So if there's no question, I can also quickly go over the Replica geometry. This will be a little bit faster. So, okay, now that we kind of construct the background, we can now talk about the replicas. And first, I will tell you before constructing them. Again, the idea is to start from Euclidean, construct them, and then go to Lorentzian. First, let me just mention a few words about like using the island formula in this setup. So we can consider it in different situations. So one situation is, okay, you have this shock waves, black hole starts to evaporate. Let's just stay in the right region and look at the regions in later times and see what the entropy is. So basically, you look at the quantum field entropy for this region R, and there will be a paradox if the entropy of your quantum fields in region R is bigger than the generalized entropy of its complement. And here, generalized entropy, you can think about it in a old-fashioned way, that generalized entropy is defined as the areas of your horizons. I mean, here you have two horizons plus the entropy of the matter field outside. So that's supposed to be the coarse-grained entropy for the complement system. And whenever the entropy of your region that you calculate is bigger than that entropy, then we have information paradox, because the whole system cannot be pure. And when you try to calculate this entanglement entropy of region R, there will be different pieces. There will be a term which is Hawking. It's like of the modes that are absorbed, or the effect of modes. Let's call them as Hawking. There will be another piece which is kind of interesting piece, and we didn't really analyze it, which is the entanglement entropy between these shocks that we inserted. This will be subdominant, and it won't be playing any important role, but it's depending on what matter you use, you can change this entanglement entropy for between your right moving shocks and left moving shocks. And there will be some IR divergent piece, because the region we consider is infinite length. And when you go through it, it will be very similar to like other contexts that people use island formula. So you have to, when you try to resolve this problem, so there will be this situation at late times when you try to resolve it, you have to consider an island. And what will happen is, in this situation, in this case, the island will have two endpoints. So there will be, one endpoint will be somewhere, and the other endpoint, it will sit at the bifurcation point. And you can, verify that the island formula gives you what you want. So basically, when you try to compute this S Hawking will keep increasing, and S black hole, on the other hand, which will be almost equal to the generalized entropy for the complement region, that will go down. And once you compute this island formula, you will see that it will appear after a certain point. So there's not any mystery about that, or any, I should say, surprise about that. And this is a slightly more general case that also appeared in these papers. The only difference from the original island paper is that here you have two-sided case, so there are more possibilities. So we can consider just region in one side as opposed to other, because we started with a finite temperature. But besides that, there's no particular surprise. I should just say that you can consider different regions. You can also consider regions that it's not only on the right, it goes all the way, like it has also the whole left region. In that case, the island will have one endpoint and it will extend it throughout to some point, but the calculation is more or less the same. And I should say that, of course, once you have this general case for finite temperature, we can always also take the temperature to 0 and get the 0 temperature, island equations and all of that. So it was just a little bit more general and easier to work with. So that's why we started with finite temperature. Other than that, it's kind of similar. Okay, so finally, let me also say a few words about constructing the replica geometry. So let's, for example, consider this case where this region R goes all the way from right to left. And then once you consider this island will also extend throughout till some point. So if you look at the complement region in this situation, it will be some region, which goes from non-gravitational region to the gravitational region. And this is easier to draw. So that's basically what happens here. So the original region was here, and then island will extend it to some point in the gravitational region. So in this case, we can try to construct the equations, and basically you replicate. So you have this psi insertion that we had, but now you also have these cuts, which tells you go from one sheet to another. And if you try to solve for equations, you again need to determine two things. One is you have to determine what's the equations for the gravity side, and you need to find what the stress tensor is. And then you have to solve these two together, just similar to the background that I showed, like the equations in the background. So here, actually, since I considered only one, I have only one endpoint in the gravitational region, the gravity part is simple, because if you uniformize these sheets, the gravity part, you can just uniformize it with a disk. So this is also something that happened in the East Coast paper. The only difference here is that you also, on top, you have also this psi operators that in Lorentzian, they will give you the shock waves, and Euclidean, they give you something else. So because you can uniformize these disks into one bigger disk, not bigger, one disk, the equations for gravity will be simple. And I should say that when I say that we want to solve replica geometry, since the topology of the gravitational part has a topology of a disk, solving just means that find this Wn of tau. So there's no modulus for the gravitational region. So the only thing we need to solve is either this W tilde, which is a uniformizing coordinate, or this Wn of tau, which is the quotient space coordinate. So that's what it means to solve the geometry. Let me
sorry, when you say disk, what is the boundary of this disk? Do you mean sphere?
No, just a disk.
What is the boundary of the disk, please?
So this part, this part is maps to this part.
Yes.
And similarly, once you put them all together, the whole gravitational region is just a unit disk.
Yes. No, but the whole geometry, is it a disk or a sphere? Not just the gravitational region.
Oh, not the whole geometry. Sorry, not the whole geometry. I didn't mean that. I just meant the gravitational part.
Ah, I understand. But the whole geometry is a sphere.
Yeah.
Thank you.
Absolutely. Yeah. And there's some details, but basically one part which is simpler to explain is this gravitational part. Because the gravitational part is a disk, we know that the equation of motion for the gravitational part will be just given by basically the Schwarzian of this coordinate, which is the disk coordinate. And we can go from the uniformized geometry to the quotient geometry. And in the uniformized geometry, the metric is fixed, the metric is hyperbolic. So you can go from like the uniformized geometry back to the quotient geometry. And there will be like, I don't know, there will be, it's like if you calculate the Schwarzian of this W tilde, there will be a term which is the Schwarzian of quotient coordinate and time. And there will be another piece which will be closely related to dilaton, but I'm not saying all of the details. The important thing is that in this setup, the gravity part is simple because it's a unit disk, and you can just do the calculation for the gravity part. For example, the gravity equations will be something like this. The part which is, again, difficult is determining the stress tensor in this background. So the stress tensor, roughly speaking, near n equals 1, if you work. For example, there will be a background piece that we determined for n equals 1, and then there will be some perturbative terms for the stress tensor. And in general, there will be two sources for this perturbative stress tensor. One is the fact that we need to revisit the whole welding problem again, because now this is a different, geometry. It's a different uh, theta of tau, or like wn of tau. And so you have a different function. So there will be a corrections due to the welding corrections. And there will be another correction, which is more familiar, which is basically now in the quotient space, you have two local operators and two twist operators. So you basically have to deal with some 4-point function, and that will also give you some stress tensor, because now you have these twist points. So you have to kind of take both of them into account, and that will give you the stress tensor, which finally goes into this equation to determine your geometry. So that's kind of the strategy. And let me just tell you the final result. So what happens is we can write down these equations to determine the geometry. We weren't able to actually solve them explicitly. And the reason for that is this welding, these corrections to welding terms, they will remain non-local. So unlike the background case that finally we had some trickery to get some local equations, in the replica case, they seem to stay non-local, so we can't really, like, it's not a differential equation that we are dealing with. Instead, what we were able to do is to integrate our equation of motion. So we have these equations and we can just integrate it, and against a bunch of kernels, which are some SL2 kernels. And once you integrate this equation of motion, some of these terms drop out because of analytic properties, and some of the terms will remain. And by integrating them, we found that basically the island formula again. So this argument of like constructing equation of motion and integrating them against some kernels, it works for any number of operator insertion, not just two psi that we studied. And it's kind of complementary to the method like, Lekowitz, Maldacena, and Dong Lekowitz, which they started by looking at the local equation of motion near the quantum extremal surface. Here, we weren't working near that point. We were always working at the boundary of disk, because to determine the geometry, and by integrating those equations, we found the same thing. But it's not like it's necessarily like more powerful or anything like that. And in fact, in the time-dependent situation, like this case, that only once the interval is at the late times there will be an island appearing. The only difference from the thing we need to do is to basically, when we try to integrate these equations, we follow a Schwinger-Keldysh contour, because in time-dependent situation that's what you should do. So in fact, when I write down this equation, it will be an integral over some Schwinger-Keldysh contour, where this will be the Euclidean direction, and then we go in Lorentzian directions, and we will find again a closed contour, just like the Euclidean. And you can apply it to that case. So that's how we find the island formula for our problem, because our problem islands are appearing in the Lorentzian time. So once you follow this Schwinger-Keldysh contour, then the integration of equation of motion gives you the island formula. And yeah, I think that's all I wanted to tell you. So I will be happy to take any more questions.
Thank you very much, Amir, for a very nice talk. Let's all unmute and thank Amir. More questions?
Amir, I didn't understand. You said there were two different methods that gave you the same result, and I didn't understand whether your conclusion was that they had to have given you the same result, or that it was remarkable that they gave you the same result.
I think they consist, like, if everything is supposed to be consistent, they have to give you the same result. The only thing is, it's we wanted to know, like, if we really solve these equations for geometry at all times, it has that information about where the island should appear. Okay. But the way we did this, by basically integrating this boundary curve on a Schwinger-Keldysh contour, and found that this gives us the island formula. So it's just a little bit, you know, you can call it a little bit more maybe global derivation, just because you work on the boundary curve and like you you find that it's not nothing is blowing up or anything, whereas the other uh, derivation works just locally around this point. But it's, yeah, it doesn't have an advantage. Like
So had you found a disagreement, that would have been an inconsistency. Something would have, you couldn't have been. Is this right? Or
yeah, so it will be that like you work near this point and you write down the equation for dilaton and the stress tensor. You find one answer, and once you like try to look, once you try to solve for the, you know, the background, sorry, not the background, for the boundary curve, you will find another, for example, solution. I mean, it's a little bit non-trivial because, for example, in these solutions, in the local derivation, there is no welding. Like the welding is not even there. Like you know, that's why like the island formula is simple, because it doesn't have like all of this welding. Whereas when you try to solve actually for the boundary curve and find the x of t or w n of tau, whatever, that one, that equation has welding. So you kind of need to figure out how does the welding drop out. And it turns out when you do these integrals, in these integrals, they drop out. So it's kind of, you know, checking that it works from different perspectives. But yeah, it's,
so the integral was removing the details of the welding solution, sort of.
exactly.
That's what you said. You didn't, to find the integral, you didn't need to know the answer to the welding problem.
Exactly.
Yeah. Okay. Thank you.
Could I ask a question?
Sure.
So there is, there is this other method of doing these Euclidean gluing problems, at least in CFT2, which is due to Cardi and Calabrese. So could you comment on like how should I think about the relation between your method where you insert these psi operators with say Cardi Calabrese? Is there a relation, or are they essentially the same, or?
Yeah, they're basically the same. It's just it's I think in that case it's way easy. I mean, it's way easier because basically in that case, uh, you know, you can have a situation that you insert this local operators, and then, for example, let's say this is the vacuum path integral, and then you can look at the entanglement entropy of some region, and you can also do the same thing on a cylinder. And in that case, you basically you have a kind of a very similar picture than this picture I draw here. Uh, the only difference is the gravitational region is also part of the flat space region. So that's the only difference. So
I see. So I
you
should
don't
think
have
of
any
the, so I should think of the psi operator as somehow the point at which these two Euclidean path integrals are glued together. It's somehow the quench point. Is that the right interpretation?
I would say I mean in the CFT case, you know, so this was the Euclidean path integral, and if you look at what they do is they create two excitations when you look at them at real time, and then they just move. So for example, when you look at the entanglement entropy of this region R, at some point this will come in. So for example, entanglement entropy will go up. But it's up to you again where you want to insert it, and it's the same was here. Like we inserted them at some general point, and yeah, and the offset again controls how much energy you're inserting.
Got it. Okay, thank you.
Yeah,
sure. So, you know, so this this QFT calculation would involve a 4-point function, as you mentioned.
Exactly.
And typically that would depend on the details of the conformal field theory. So it's not universal. So presumably you would take some limit in which it factorizes, or what happens?
Yeah, great. Yeah, what will happen is they will factorize. Like when you look at this problem at very late time, and this region R is at very late time, they effectively factorizes, and you can just use the factorized answer. And there are, depending on your theory, like if you have large C CFT, or if you have like I think massless fermion, and this psi insertion is something specific like vertex operator, I think you can calculate it explicitly. But for our story, what will happen, like the effect that you mentioned will be something like this, that when I write this was the factorized answer, that there was a shock and there was a Hawking. And it's not clear from what I told you, but what will happen is when you go through like this delta goes to zero limit, that delta goes to zero limit actually will be the OPE limit. But so because if you remember, we send them to zero, and that sending them to zero basically it's reducing the problem of calculating this 4-point function to OPE limit, although it's a little bit it has some technical issues, that like whether you're in first sheet or second, like you have to be careful about like branch cuts and these things. But at the end, what will happen is when it factorizes, you have these two pieces, and it will factorize because of this OPE limit. So in that sense, it's universal. But yeah,
Nice.
Yeah.
So at late times, at late enough times.
Yes.
Okay. The other question is that
I think as far as the delta goes to zero, I believe after a certain time you will be in the OPE channel, I think. So I don't think for that you need a late time.
So that time is given by what?
I think it's right after the shock enters, actually. I don't think there's a like
Nice.
there will be another there's another case that I told you, which is this case. This case is more complicated because your region has two endpoints, the island has two endpoints, and on top of that you have these psi operators. So this case you're dealing with 6-point function, so things are more complicated. But for this case, that basically effectively your region and island will reduce the problem to like an interval and operator insertion. I think right after the shock waves, you will be in OPE limit. So at least for delta goes to zero limit, this will be valid, I believe.
I see. This is all worked out in your paper.
Yeah. I mean, we didn't really expand over the OPE limit because it's like if you look at the local quench papers from like 2014 and I guess maybe even before that 13, people like worked out this example of operator inserting and like careful about like cuts and like limits and OPE limits. So we didn't really expand on it, but yeah, it exists in the literature.
Yeah, no, that I seem to remember, but there I thought I thought that you needed late times, but you're saying it's something instantaneous after the maybe I should look at those papers.
Yeah, I mean, if I'm not mistaken, I think for the case of one interval, yeah, you will be in OPE limit right after the shock.
Right. Okay. Okay. Thanks. The other, yeah. Oh, yeah. The other thing is that you talked about fermions, let's say, as a constituent thing for the bath. Now, don't you have an idea, or if anybody who does this, bulk plus bath models, that the matter field in the bulk region, in the ADS region, is the same matter field, of course, as in the bath region, let's say, but the matter field in the bulk region can be understood as dual to some CFT operator in the boundary theory. In the what I'm saying is that this matter field in the ADS region is some natural matter field in the ADS region, which has an ADS CFT dual, etc. Right. So if
that's an excellent question. I think the only case I know of is not answering your question, but it's kind of getting where you want to go, that like construct a matter field inside the gravity region from the bath point of view, or like some SYK maybe attached to it, was in the West Coast paper that they have this end of word brains. And in that case, I think they have some explicit formula in terms of PETMAP for constructing like excitations inside from the point of view of boundary. And it's a great question of like, what's that construction here? Like how to like construct those like fermions inside the bulk from outside. And I don't think that's been done in a very explicit way.
Yeah, I also don't think that we are trying something like that, but I just wanted to know whether you know of any other. Thank you.
Yeah, no, I'm not aware of that.
Right.
Any construction.
Thanks a lot.
More questions? If not, let's thank Amir again for a very nice talk.
Thanks,
you.
Amir, for a wonderful talk.
Thank you.
Yeah, I mean, it was really, really, really nice. Thanks a lot.
Thank you.